Hi, I'm Jorendorf, and it's December 16th, 2018, and I'm about to solve today's Advent of Code puzzle. I've got a blank terminal here. I'm going to solve this in Python, and an empty program over here. And I've got my coffee, so I'm ready to go. Let's see. This one's kind of long, so I'm just going to read every word. As you see the elves defend their hot chocolate successfully, you go back to falling through time. This is going to become a problem. If you're ever going to return to your own time, you need to understand how this device interface works. You have a little while before you reach your next destination. With a bit of trial and error, you manage to pull up a programming manual on the device's tiny screen. According to the manual, the device has 4 registers numbered 0 through 3 that can be manipulated by instructions containing one of 16 opcodes. The registers start with the value 0. Every instruction consists of 4 values, an opcode, 2 inputs, and an output. In that order. The opcode specifies the behavior of the instruction and how the inputs are interpreted. The output, C, is always treated as a register. In the opcode descriptions below, something says value A. It means to take the number given as A literally. This is also called an immediate value. Something says register A. It means to use the number given as A to read from or write to the register with that number. So the opcode add I adds register A and value B, storing the result in register C, and the instruction add I 073 is encountered, it would add 7 to the value contained by register 0 and store this in register 3, never modifying registers 0, 1, or 2 in the process. Many opcodes are similar, except for how they interpret their arguments. The opcodes fall into 7 general categories: addition, multiplication, bitwise, and bitwise, or assignment. Okay, so add register stores into register C the result of adding the 2 registers A and B. Add I stores in C, register A plus value B. Multiply register is register A times register B into C. Multiply immediate stores in C, register A times value B. Bitwise and, with convenient link to Wikipedia, stores into register C the result of A and B, both registers, and then register and value, blah, blah, blah. Same thing for bitwise or. Set R copies the contents of register A and register C. Set I stores value A in register C, and input B is ignored. Value A. All right, cool. That's weird, but okay. Greater than testing. Okay, wait. Input B is ignored. Okay, great. All right, great. Greater than testing. GTIR, greater than immediate register, sets register C to 1 if value A is greater than register B. Otherwise, register C is set to 0. GTRI greater than register immediate sets, okay, great. It's the opposite. Okay, got it. And then GTRR compares to registers, sets register C to 1 if A is greater than B. All right. Equality testing. Same deal. Although, why do they have this one? That's odd. Okay, unfortunately, while the manual gives you the name of each opcode, it doesn't seem to indicate the number. However, you can monitor the CPU to see the contents of the registers before and after instructions are executed to work them out. Each opcode has a number from 0 through 15. The manual doesn't say which is which. For example, suppose you capture the following sample. This is a neat puzzle. The sample shows the effect of the instruction 9212 on the registers. And this one's modified. So let's just think this through without reading it. This is an instruction that managed to change this one. This is register 2, and which conveniently is the one specified in the output. But I don't think there's any, like, okay, so they can't both be immediate, but that wouldn't make sense anyway. This has to be a register. So register 2, do something with register 1 or the number 1. I think it's the number 1. I think it's add immediate is what this instruction has to be. Okay. The instruction itself means that opcode 9 was executed with A equals 2, B equals 1, and C equals 2. Opcode 9 could be Muller, register 2, which has a value of 1. Okay, cool, times register 1, which has a value of 2, produces 2, right? Or it could be add I, which is the one I thought of, or it could be set I, where you just take this value and plunk it into this register, and that's what happened. And the number given for B is irrelevant. Okay, none of the other opcodes produce the result captured in the sample. You collect many of these samples. The first section of your puzzle input, the manual also includes a small test program, which you can ignore for now. The second part of your test program. So ignoring the opcode numbers, how many samples in your puzzle input behave like 3 or more opcodes. Behave like, oh my gosh, this is so great! Puzzle input, boom! So there's a like 3-line break in the middle. So I'm just gonna like read the whole thing in, and then just split it on 3-line break. I think that's right. Yeah. I guess it'll be 4 new lines in a row. I think that's better to do that way. All right, great. So first of all, like, does that work? Oh, no, it's not terminal. Yeah, that so far so good. All right, then okay. So I mean, I can take this as an example. Should be 3, right? And then after that, all I have to do with the input is yeah, I mean, you know, if how many opcodes does this thing resemble, then is at least 3. Is at least 3, right? 3 or more. Okay. Then add 1. Print total. That's the whole thing. Well, we just need to actually write the program part of the program. All right. So what are the lines? Let's just do an exact match. This is always, like, regular expressions are always a high wire, but I just like, sometimes they're just the right thing. I like, ignore white space at the beginning, go for before. This is a multi-line regular expression. Let's actually put that at the beginning where it belongs. We're going to before colon space, and because, oh my gosh, okay, yeah, because so actual bracket, 3 of those, right, followed by a digit, actual close bracket, new line, and then digit is that, like, this is the opcode, and the 3. I'm like, oh my gosh, I'm actually put them separate groups. This has to be an X. X means that I can insert white space in here. Okay. And a new line, and then 4 digits, and then after. Right, same exact deal as there. Followed by white space and the end. Right. This is. There's no way this could possibly fail. Okay, except if I passed the wrong number of arguments. Okay, great. So that failed, like, instantly and completely. So the way I usually debug regular expressions is, like, not very fancy. I just delete some of them and, like, see if it matches, and binary search to just try and find where the problem is. Oh, different assertion this time. All right, so that means that this part matched. So it was this first line. So I'm matching a group consisting of. Let's go back and look at the input. It's skipping white. Okay, great. Obviously, there's white space here, and this is an actual literal space. Same thing here. Ooh, gosh, so inconvenient. Yep. All right, so then this is space. Let's give it a shot. Okay, good. So now it is parsing, and the assertion fails because it returns none instead of 3. Okay, great. So this passed. Excuse me. So what are the actual groups in here? Well, I had one before the 4 parts of the opcode and then the after. So that should work. And then this is totally terrible, but I mean, what are we trying to accomplish here? We're not messing around. Okay, great. So now we, oh yeah, and then I mean, I could just say eval for all of this. So, somehow, how terrible is this? I'm just gonna map them all through eval. This is the worst thing ever. This is actually safe because the regular expression already confirmed that they're gonna match specific Python expressions that are safe to evaluate. Okay, great. So, right. So now I have to actually test against all the possible opcodes, which is kind of a pain, and then keep running total. Is there an easier way to do this using Python's dynamic features? Probably so, but I can't think of what it would be. I mean, it feels like the assignment ones are going to be totally special. So let's do those. So setR is going to copy the contents of register A into register C. It's going to take this stuff and it's going to spit out. It's going to spit out regs with register C replaced. I don't know. Oh. Make a copy of my list. So I'm making a little function because I want to do this in a kind of functional style that just takes a list, creates a new list that is a copy of it with one value change, right? And so that's what I'm going to use here. We're going to replace the registers by changing index C to have value A, register. Ooh, value in register A, so regs A, right? So that pair, that's one opcode, and then set immediate is the same thing, except instead of the value of register A, we just pass the value A, right? But then there are a bunch where register A is never immediate. Register B may or may not be immediate. So I mean, I would probably be better off at this point just writing the stupid thing. Do they all modify register C? They all modify register C. There's no jump instructions in here. This is stupid. Okay, so they all modify register C, which means I don't even have to include register C in the protocol, like calling convention of these opcodes. So I can ditch it. ditch the replace thing, and we're gonna like register A. So that, oh, this is great. Oh, this is so much better. All right, great. So I have A and B. Great. Okay. So so what I'm gonna do is like instead of using Python's programming features, I'm gonna use like you're not gonna like this. I'm gonna use Emacs's editing features. So I'm adding is plus, multiplication is star, bitwise and is the ampersand, bitwise or is the vertical bar. We did set, oh, not greater than. Is greater than good? Like, can we, yeah, that's good. Okay, so GT. There's a problem, though, which is that this one doesn't behave quite like the others. Leave it alone. I just, whatever. It doesn't even matter. Greater than, and then EQ. So equals. All right, great. So what I'm going to do is I'm going to, for each of these, I'm going to use multiple cursors to do this thing, where I then delete that word, paste it back, add a letter R, and lambda regs A, B, something here. I mean, it's going to be, all of these cases, we're just like taking the value of register A, and then we're using that operator, blah, 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 value of B, right? Right? Actually, that's it. But I can do, oh, shoot. Okay. So far so good. I think, right? I think this does the right thing. This is what I want each opcode to do, is compute this value, right? But then there's another thing I want to do, which is, so make a copy of it, except this time change this R to an I. Oh, we already did the immediate version. We want the register version. Okay, so this is the one we need to change to registers, right? So far so good, except that like the G, like what happened? It like came out in the opposite order or something. I like reversed the order without noticing. Wonderful. Okay, great. So then I'm just kind of I don't know what the heck just happened, but it happened anyway. So then these I got a little bit wrong. So I don't know what happened here. So again with the cursors, and now what I want to do is I want to say, okay, so this is for GTRR and EQRR. I think this is actually exactly right. Now for here, GTRI, this is correct, but we don't have one for the other case. So what I'm going to do is kill, paste. Okay, that didn't turn anything upside down. I still don't know what happened. We're gonna go over to the side here, and this is gonna be like that. Okay, all right. So this should be pretty much it. I'm gonna probably try and put them in the order that they are in the document, just like to make sure that I have all of them, because otherwise I'm gonna have weird bugs that I don't understand. So here's add. Where's mul? I could have typed this in by hand though this time, but it was so much fun. I don't regret anything. And an or. Okay. Assignment is set R and set I, and then the greater than equality testing. Good. We got all the opcodes. This is good. Okay. So now, so then the I mean, we just want to return the number of these that that actually seem to work, right? So we're going to replace the registers before at index C with the value that we produce by calling the function, passing it registers A and B. And then if out equals after, right, then total plus equals 1. Let's run it. None-side logic has no, okay, great. So something didn't match. If m is none, print s, and then we'll like the same way. Okay, great. So this failed to parse, and it failed to parse because I only allow 1 digit here, and it should be like 2 digits or like any number of digits. So Great, so far so good. 493. Let's see if that. It was kind of. It's always an anticlimax when one of these runs instantly. Okay, great. So on to part 2. Using the samples you collected, work out the number of each opcode and execute the test program. What is the value contained in register 0 after executing the test program? That's so cool. All right, so I need to work out. Great. All right, so how many opcodes is really not. What this is doing, what we're going to be doing here is this is going to be computing kind of constraints, and then we have to solve the constraints. But basically, at the beginning, any number 0 to 6 to 15 could be any opcode, and then we can narrow down from there. So let's say this is part 2. I've noticed a mistake I make every single time is I always run the old one first before running the new one. So I'm going to do that. Go ahead and get that out of the way. Right. So so now I guess I have to change this. So which opcodes are possible matches? And it's going to return a set. It's going to return a set of possible opcodes. Yeah. Right? Check this out. Because Python is so great, because I happen to have a list of pairs, I can have these, I can make them in a lookup table and I can look them up by name. Isn't that cool? All right, great. So what this is going to do is going to return all opcodes. It's just so great. Yield the name. Like, we're done. So this yields all opcodes. That that could possibly match, and so in this case, for example, mol r. I'm suspicious of that mol r opcode. I think we need to have a mol r investigation. Let's see. All right, so this should work, but what we're doing in the end is not this. We're doing something to that, but I don't know what it would be. So, comment it out. The assertion fails because I did something stupid. Yield name is what I'm doing. Well, let's see it. I really wish Python. I'm gonna hack Python. Okay, add I mul r set I. Oh, they're in just a different order. Fine. Great. So I used the wrong data structure. She's a set, right? Okay. So far, so good. But what I need to do is each time. It doesn't give me any sample stuff. I just really need to work out for myself. So so the possibilities are for 0 to 15. The possibilities are basically all of the names. And we call that opcode table.keys. All right, and then yeah, so this is so bad. I can't get over this. We're just gonna yeah. I'm going to parse a sample. Which opcodes could the sample match? Blah, blah, blah. Okay, great. And then, so for each sample, we're going to parse sample. And then we're going to, we're changing the type. That's because that's something we do. Okay, then which opcodes sample? Oh, no. It's not like that at all. Instead, the op is sample 1. And what we're going to do is we're going to disable, we're going to remove we're going to remove the ones, okay, well, yeah. We're going to AND it with, except I need a copy now. Opcode. Copy. Yep. Okay, great. So we make the set of all possible all opcode names, and we're going to copy it for each one in range, and we're going to modify each one. What we're going to do is like remove the ones that are not in that are not possible, right? We're going to remove the ones that are not possible. So we want the set of the ones that are. Yeah, this is right, right? We want to. Is that right? So we want to eliminate all the ones that are not in that set. Yeah. Okay. Good. Okay. Great. So then, at this point, I just probably want to see it. Let's see it. Too many values to unpack. Expected 6. Oh dear. What did I do? Did I mess with the regular expression? I didn't do anything. Come on. I didn't mess with this regular expression. Like, do I have to read this thing again? Like, what? Okay, parse sample. Okay, great. So I'm passing a string instead of passing the parse. No. Oh. Okay, right. It's my test. My test is screwing me up. See? Okay. All right. So I got to the end, and I still had too many possibilities, right? So I've obviously got some kind of a bug in here. So the first part passed, which makes me have like some confidence in this code. But I obviously screwed up this code. Okay. So let's just slow down a little bit. Each time we parse a sample and we run the sample through the which opcodes thing, which gives us the set of all opcodes in our list that might possibly match. We're redoing a lot of work here since we don't. Yeah. Okay. So this is the okay. So all right. Well, let's. Oh. No. Sorry. I was thinking. No. We're supposed to be using part 2 of the puzzle input. We're not. We're supposed to be using part 1. Maybe this is the problem. Like maybe I've forgotten. Maybe I don't know what this is doing. And equals is supposed to be reducing the set to only items that are already in the set and already in the right hand side. So I think that's right. I'm gonna stare at it a little bit more before I like debug some more. Well, I can always print the sample and then show what we think is the case. Geez, that could be anything? Really? Oh, yeah. I got like a lot of things. GTR. Yeah, this always like, okay, good. But this one only a few things. Oh, wow. This is just fascinating. Okay, but here, modifying this register, it could be bitwise and or set immediate. Yeah. I mean, this is right. It's right. Like, I don't know. And then what happens? I mean, just like the sanity check. Okay, good. The op is correct. I don't know. Why do we have too many possibilities left over at the end? That is the critical question. Like why? This is like very simple Venn diagram BS that I should be able to do, right? Like this is not hard. It's literally like 4 lines of code. I've got a bug in here somewhere. I don't know what it is. Maybe. I don't know. Like maybe I have a bug in one of my. Okay. All right. So let's do this. Is the culprit? So like this. Right. Once one of them is down to 1, we can eliminate it from all the others, right? So like, Oh my gosh, this puzzle's better than I thought. All right, so okay, so great. So we got once we like now that Mulai is we know Mulai is opcode number one. This is 0, 1, 2. We know Mulai is opcode number one. We know Borai is opcode number two. We can remove those items from all the other sets. Like they're all finished, and we can repeat that until we get down to a unique solution, right? Um, Boy, I hope this works. All right, so infinite loop. Like once again, like I always feel uncomfortable when I'm like, I don't know if this is going to terminate or not, but let's just go forever. But I don't mind. I don't mind doing it in this case. So for index and working set in possibles. Oh, in enumerate possibles, right? So we're going to go just loop through this. We're going to do it repeatedly until while not all they're not all unique. Like while we have not reached the solution for S impossibles. Great. But again, there's no guarantee that this is going to work. We're going to go through. We're going to for each if length of is 1, then what we do is we're going to eliminate it from all the other ones. So for if j is not I, and okay, so right, so and item is in SJ, remove it. I don't know why Python's so picky. Yeah. Okay, great. So this should do it. Yeah. Great. And then I'll print it out. Oh, look at that! What? Okay, great. So then, actual opcodes is going to be for each of these sets. It's going to be the one item in the set. So like that. Let's try it. Oh, I didn't print out actual opcodes. Look at it! It's so pretty! All right, now all I have to do is run the program in the second half. So for line in program dot split lines. I'm going to strip it first, just in case. I don't really know. All right, and what do those lines look like? They are 4 integer fields. Right? And we get the number, not the actual opcode. But what we can do is we can get it. Now that we have this list, right? And then we can look that up in our opcode table. We'll look that string up in our opcode. So this gets the name. This gets the function. And we start with registers 4 zeros. And okay, right. So we actually have to execute opcodes again. Like I'm not going to comment this out because I'm not that interested in it. We're going to replace within our current registers register C with the result of calling the function, passing it the registers A and B. Again, we're kind of working without a net here. It doesn't give us any tests, but let's just see. It'd also be kind of cool to read the program. Oh my gosh! What? It'd be cool to kind of read the program and see what it does. But since there's no control flow in this language, I guess it's straight line code. Let's take a look at it. It's already here. Okay. It's kind of long. Well, that was a super fun puzzle. Okay. All right, so that's a program. Well, this is great. I hope you had fun, and I'll see you next time.